Okay. I have to start all over again because I forgot to start recording this thing. So today we're going to be looking at the inverse of a square.
Mona,
Yes?
sorry to interrupt you, but I think there's a message you should read in the chat.
Okay, sure. Oh, guys, it's the same password. Yeah, it's the same password as the same thing. For those that are not able to use the link, it's the same password. Yeah. Sorry, let me just do this. Okay. All right. So inverse of a suite is basically just 1 over the particular suite, the suite UN. And what happens is that we know that UN already has a limit of, the limit that normally is used is L, and that we already know. Meaning that if your suite is already in inverse, meaning even the limit is going to be inverse. This is why here it's 1 over UN, and that's equals to 1 over L. Yes. Because this is an inverse, meaning yeah. So that's that on that part. Yes. So here it says we have a suite UN, and this same suite it's positive. Yeah. And we know that it's positive. This is for this suite here. Here it says it's strictly positive, that we already know. Then it says if the suite UN is heading towards L, meaning that this L should be greater than 0. It's for this reason why it's also can be equals to 1 over L. Because definitely 1 over L, this L can be anything here. And when you divide, it should give you a number that should be greater than 0. We already know that this entire suite here is already positive, so it really can't be. So even just by you guys knowing that this suite here is positive, we know whatever answer it should give you is going to be a value that's going to be greater than 0, because already we all know that okay, it's already positive. That already sells you out and tells you rather defines what this 1 over L is actually means. Yeah, and all. So we're going to look at the demonstration just as usual. They always have to show us or rather define what this is, so you can at least understand it further and deeply and everything else. So when you have a suite UN, remember last week they had involved the suite VN and they had involved the suite WN. But this time around, we're going to look at the suite UN because it's a suite UN that's the inverse that has been divided in this case here. That's our focus today. So what happens is just like usual, we have to redefine it for us to know why it's like this and why is it that no, here they put the L, and what happens when this is like this. This is now why this entire data here has been given, so you can further understand exactly what's going on. So a suite UN, it has a limit L, and just as we were told at the very beginning, this suite is positive strictly. As usual, we have an N, a capital N, and then the same capital N is a member of natural numbers that we know. We know that the small n is always going to be greater or equals to the capital N. Remember that the small n the small n comes from the suite UN. Why? Because the suite is in function of n, small n, not capital N, but then small n. We know this already from the last time. We've seen it over and over again, where we know that the modulus of the suite. The person in the microphone on, please. Sorry. Thank you. Yeah. So we know that the modulus of the suite UN minus the L. This L here represents the limit where it's heading. Whatever it is we find here should be less than the L over 2. So this here is a condition when you've been given this. One thing you come to realize is that this part here, this definition, normally like when they involve the suite and when they involve the suite and its limits, it's different from the other ones. At times it can be the same. Like under quotient, the sum, yes, quotient was different, sum it was different. Even this time around as well, it's different. This time around, it's saying that whatever it is you find here, your value should be smaller than the L over 2. Yeah. And then it goes on to say that, meaning that the suite UN should be greater than L, which is, that makes sense. Should be greater than the L minus the L over 2. This L as well can be any number here, whatever it is, as long as it's a real number. You can put whatever it is here. This suite UN here can be any fraction, as long as it's in fraction of n. That should be how it's supposed to be. Yeah. And then whatever it is that you find is going to be equals to the L over 2. So whatever value you put here, whatever it is. But basically why this is here is just for them to give us more information on more info, so we know exactly what's going on under the inverse of a suite. Yeah. So first and foremost, the first thing we have been told is that this suite one is positive. That's one we know, it's positive. The second thing we know is that, as usual, that there's a small n and a capital N, and the modulus of the suite minus the L should be less than L over 2. This case here, we are dealing with fractions. This is why we have L over 2, 1 over L. We have again L over 2 has been repeated, 1 over the suite UN, the same thing over and over again. That's the whole concept in this case here, because the inverse is basically just division. Yeah. So, oh shoot. Yeah, so that's this part here. Yeah. So yeah, so here it says that the suite 1 over the suite, so the inverse of a suite should be, the inverse of a suite should be less than 2 over the L, and then this L here represents the limit of the suite UN. Remember what I had said last time? Whenever they involve the UN, the suite and its limits, like together, and maybe they say the suite plus the limit. Meaning in this case here, this whole part here is going to have its own limit, like under normal circumstances. Here to have its own limits. Yeah, and like here. Sorry, just hold on, give me a second, guys. Yeah, so as I was saying, normally when they involve the suite and its limits, like the way it has been involved here, what happens is that it's going to, like, under normal circumstances, like if you've been told to solve this thing here, it will have its own limit, because it will have its own limit. Maybe the limit can be the same value of the initial limit, but yes, yeah, because in this case here, these two have been involved, they're like in an entanglement. So yeah, so this part here, yeah. Then just as usual, they have to tell us, they have to like redefine everything. This is why we have n is greater or equals to the capital N, and then we know that the suite UN is going to be majoré and going to be born and it's minoré by 0 and everything else. Yes, but otherwise, this first part here, the whole concept is for them to introduce an inverse of a suite, so that they can tell you that it's possible for your suite to be inverse. And what does it mean when your suite is inverse? First and foremost, we're going to look at the condition where where the suite is positive. When it's positive, we know that, okay, meaning that whatever value we'll find at the end should be a value that should be greater than 0 under normal circumstances. Why? Because you know that your suite is already positive. Unless maybe the fraction is -1. Yes, maybe like it's -2 over that. We all know how a negative always, it surpasses over the positive whenever you're looking at mathematics and physics to whatever. Yes, yeah. So that's that there. Yes. And then we also, and then what happens is now, in this case here, in this case here, they have multiplied the initial sweet, which is one over the sweets, and then it's been multiplied by the redefinition of the sweet in the other way, which is the un minus the l. The un minus the l. And then here they say that the product of these two sweets which are born has a limit which is heading towards 0. So just as I said, the way they've involved this, the way they've involved, they've brought about the initial sweets and the redefined sweets. This as well is a whole other sweet. This sweet here is different from this sweet here and different from this initial sweet here. So this sweet here, if you've been told to calculate it, it will have its own limit. This one here has also been redefined. It's a new sweet, meaning it's a new question, and therefore this is why it has its own limit, which it's heading towards 0. So always note that whenever something is redefined, a fraction is redefined, or a sweet is redefined, mean that even its limit as well is going to change. So that's that. And so that's basically that. Let's see, the other things, the same thing. They get this here, it says no, it's equals to 1 and whatever that. Let's see. They've just done some calculations there for them to find this other part here, and for all that, and everything else, 1 over the un there, heading towards 1. Things here have changed. Here is now heading towards 1 because they found that there, and everything else, and all that. Otherwise, the whole concept of them showing you all this is such you know that there exists an inverse of a sweet. There exists when they give you, when you have to add sweets, when you have to multiply sweets. All these things are possible, and all these things, they can be solved a particular way. So that's that on that part there. Yes, let me see. We have a preposition here. We have some preposition here. I have a sweet un, which is strictly positive, but then this time around, strictly positive, this one here. Then it says that if the sweet is heading towards positive infinity, meaning 1 over the sweet un will head towards 0. This here is a condition. According to this here is a condition. The same thing with here as well. According to the condition here as well, the same thing here. If the sweet un is heading towards 0, that means here the given has 2 conditions. If your limit is infinity and your limit is 0, when your limit is infinity, that infinity has a charge of it being positive. What happens is that your sweet becomes an inverse, and this time your sweet is, and this time the sweet is going to, the limit will change to it being 0. But then when your sweet is 0, the inverse of the sweet is going to be, so the inverse of the sweet will have a limit of infinity, which is going to be positively charged. So that's that. And then just like any other question, whenever they give you a proposition, they always have to redefine it. Gosh, this flies, why? They're always going to have to redefine it and everything else, which is this part here. Here they brought about epsilon. Here they brought about epsilon, just brought here, and just hold on, let me see. Ish. Comparison of sweets. See how far I go in this. Guys, just hold on, give me a second. Undo. See how far I'm going. Okay, so I'm actually not far for finishing. Let me finish this ASAP because this is that we need to start doing this. Yeah, function of real variables. Yeah. Oh my goodness. Okay. Mm, okay. Yeah. So for the demonstration or for the redefinition of the suite, in this case here, they brought about epsilon. So they said epsilon as usual. We all know it's going to be greater than 0. That we all know. It's fixed. Like we know that. Yeah. Then this time around, they say the limit is heading towards infinity. The answer will give us infinity. Then, as usual, we know that n is going to exist. We know, as usual, the small n is going to be greater or equal to the capital N that we know. Then, in this case here, the first definition is that your suite is going to be greater than 1 over epsilon, which is just usually just by definition that we know, because you know what epsilon means and all that. This here is already very obvious. Yeah, and then we go on to conclude that 0 is going to be less than 1 over the suite's obvious, and this 1 over the suite UN is going to be less than the epsilon. Yeah, so just when you just look at this, it makes everything else very obvious, because we know what our suite is, we know what epsilon means. So all this, so this other definition here, it's very obvious, very, very direct. And yeah. Yeah. Let's go on. I need to just show you guys. It's my book. Okay. Yeah, so that's on that part there. And then just as usual, like you remember how the initial suite here was just UN here. It was just UN. Then the limit was infinity, right? Yeah. This time around, what has happened here? They put the inverse. Yeah, they put the inverse of the limit. And remember, when you look at it on top here, what happens? What did they say on top? What they had said is that, sorry. Okay, yeah. So what they had said is that they said if your suite UN, the limit is infinity. The moment that suite becomes an inverse, the limit will change to be 0. Then when instead of the limit being 0, they mean that your inverse, the limit will also change, just as it has changed here and here. So that means here we've been given 2 conditions here, and everything and all the conditions that have been given here, we are going to apply them here. And therefore, that is why this suite 1 over the suite, 1 over UN, the limit here is 0. Sorry, there's someone whose mic is on. What's up? Do you have a question, please? We don't have a question. No? The person with their mic on. Okay. All right. Yeah, so that's on that part there. Then just as usual here, we have our K. We have our K. We all know K is a member of real numbers, and we know what K is. What does K represent, guys? From last time, I think K has been introduced a number of times. So what does K mean in this situation? Well, under general circumstances, what does K represent? Someone to answer? Anybody?
It represents a number. Question.
Huh?
I think it represents what is the maximum.
Yes, exactly. The maximum, yeah. That's what your K is. And the maximum normally should be a member of real numbers. Yeah. So here, our limit here is heading towards infinity. And the answer there is equivalent to 0. And here it says that the suite is gonna be great. I mean, the suite is greater than 0. Sorry, just sure. Yeah, I mean your suite will be greater than 0. Yeah. And then just as usual, remember when you're defining something, you always because we have the n, and because a suite is un, this is why you're constantly redefining the suite, constantly saying no, the n is a member of real numbers, no, the n is greater or equals to the capital N, and then therefore the capital N should be a member of natural numbers. This is why you have to redefine it, because in this case here, unlike where they give you a question, here they've used letters to explain the work. So they have to at least give you guys a perspective on whichever thing they've put here, what it actually means, so that you are able to fix whatever value you want, whatever value suits for you, and makes the work more comprehensible for you to actually understand and everything else. This is why they have to redefine the work over and over again. This is why you see so much of no, n is greater than this, member of what. It's that you as an individual can put whatever values you want, so it can make your work easier. Because let's say, for example, either to put, maybe they put the value 7, not everyone is going to understand that no, 7 whatever it is. Others will take it as no, 7 is the only number that's going to be whatever. Yes, yeah. This is why they made work a little bit easier by them putting these things, putting the n's, the l's, whatever instead. So at least you yourself, you put whatever value you want there, that makes work easier for you as an individual. This is why it's like this. Yeah. Actually makes your work much easier. Yeah. So that's that. Yeah. Then just as someone has said, what the K represents, it represents the maximum of a particular switch you've been given, and that whatever value you've been given, that's a maximum, should be a member of real numbers. This is why in this case here, they just concluded, they have said K the member of real numbers, and we all know, like from before, we know what the K actually means and all that. Yeah. So this part here has come all over again. And then now in this case here, what has happened is that, unlike this one here we're looking at the epsilon. In this case here, they introduced the K. And what happened? This case here, what was the inverse in here was the suite. This time here, the suite is not an inverse. What happens here is that the K has now been put, it's now the inverse of the K. This is what has happened here. So these are the changes here that we can actually note from these two, where they use the epsilon to explain this, and when they've used the K to explain the 2 points that you've been given under a suite being strictly positive when it's not an inverse. Yes, by definition. Yeah. So
I have a question.
yeah.
On this one, that was that the one that is heading towards 0. Does it
The
mean
first,
does it mean that he doesn't have a constant, the maximum?
the what?
Does it mean that it doesn't have a maximum or what?
For it to head towards 0? No, it will still have a maximum. It's only the limit that's 0. What would determine its maximum is going to be what you find at the end of the day. What switch you've been given. The limit didn't have anything to do with a maximum being involved or not, or it not being involved. What determines the maximum being involved is the kind of question you've been given, not the limit. So yeah, not the limit where the suit is heading. Yeah. Huh?
I was saying it's fine, Nambeda.
Okay, all right. Okay, so that's for that part there. Then yeah, so here it was the inverse in this case. So happened is that, so here they say 0 will be less than the sweet, and the sweet will be less than 1/k. Yeah. And here it's actually sort of very obvious that a sweet should be less than 1/k, because already you know that your k is the maximum value of a particular sweet. And when you do some calculations, it should probably, like, whatever value you should get should be actually a very big value. And that's how we know that, yeah. So this is for this, yeah, for this part here. And even just when you even think about it, here they say that the sweet should be less than the inverse of k, meaning that if we are looking at the k itself, it not being inverse, meaning the sweet should be greater than the k, because when it's inverse, the sweet is less than the k. This is why it's like this, because already when you've been given this, automatically you know that, okay, no, because it's an inverse here, it should be like this. If maybe let's say here if it was 1 over un, the sign here will change. And if this k was like, if it was just k, not the inverse of k, yeah, the same thing here. Here this comes on top, the one has been going, okay, they swap positions, the sign changes. The same thing here, just like that. This is how you are able to formulate things. You know, okay, no, this is why it's like this, because from here it was like this, and if you do what, it's actually like this, and all that. Yeah. Then yeah, so, and then in this case here, your limit here was 0. So your limit here is infinity. This one here, your limit here was 0. So just like this, just like the initials we were given, the a and the b, in this case here, when you're trying to when they're trying to redefine what they gave us here, what they chose fit for them to use for us to like understand or at least have an idea of what's going on, is they brought about epsilon, and they brought about our k, for them to try to find a way to at least give us an idea on what's happening, and to just for them to be able to introduce other values, other letters, and the sort. Yeah, so this is for this part here. Yeah, well. Yeah, so before I go any further and go on and look at these other properties and everything else, guys, normally under suites, you really have to focus on the suite arithmetic, geometric, and yeah, those things are very, very important. But even these very prepositions too are also very important, like more or less for those who are going to do things like ENSA, ENSAM, GGM, MIC, MIP, and yeah, where the analysis goes deeper. Yeah, where the analysis goes deeper. All these things that are being explained right now, you actually are going to apply them and use them. And like for those who are going to do BCG and sort, there the analysis is more on the surface. Yeah, it's more on the surface, but still very, very understandable. Yeah, so quite right, you still have to like go through the propositions you've been given and all that, but then your professors might not really like actually look at them like one by one and explain them and say, no, this what, the way like they've been explained in this PDF here. But otherwise it's still very important for you to actually know all these prepositions, how this and this is actually possible for it to be like this, because there are times maybe like a question you don't understand the formulation, but then with time, but then like you read through the notes, to be easy for you to actually like know what you've been given. Or you said and business, for business, the analysis is different, because there you're going to be looking at, it's like you're looking at business and mathematics. So there, and it's not that deep compared to other things. Yeah, it's not only just maybe like a small part and all that, but it's not that deep. Yes, yeah, and all that. But I'm not so into the business sector. I don't have much info there, but it's not that deep. Yeah, it's not that deep compared to how it's deep for how it's due for PCG and these other subjects. I didn't give you guys topics. Oh, I didn't really. Oh my goodness. So sorry. I thought since you guys had your first class with Ernest, I thought he already gave you guys the topics. Oh my goodness. If you don't say. Ish. Ish the streets. You guys don't have topics? Okay. Anyway. So the first topic is the first topic is real numbers that we already did, and then suites, and then sorry. Oh, okay. Okay, so now for Apeza as well, for Apeza, there you actually do the analysis just like it's done like in the it's more detailed there as well, just like it's done like in this in these other what you call this other courses. Yeah, it's detailed as well. Yeah, Apeza, it is detailed too, so you have to make sure you actually do, and you actually like do see the properties and everything else. Yeah, because it's detailed. Apeza, it's detailed. Yeah. Okay, so he gave you guys the general topics. EST. What's EST? Sorry, I forgot. Then just hold on. Let me wait. Hold on. Let me ask. Oh, I didn't say GGM. GGM too. GGM because you guys can actually. Oh, sorry. GGM. There's Analyse 1 and there's Analyse 2. BCG. There's just Analyse. Then yeah, me there's Analyse 1, 2. MIPC should be the same thing. Yeah. Sorry, let me just read through the questions. Okay, SVT is I'm not sure about SVT, but I think the analysis is not that deep. Yeah, and all that. I think it depends with your professor. Can you kindly give us an oral example of these prepositions so that we think in line and try to understand them? Okay. All right, I'll give you guys an example. Yeah, in theory, I guess. Yeah. Otherwise, yeah, these things like you actually like do have to like try to understand them, because they help you like be able to apply the work like in what you're actually going to do like in front and all that. Yeah, so you actually like do need to like actually like go through the work and everything else. Yes, yeah. But normally like what you really just have to like is like you have to know how to look at suite arithmetic, suite geometric, suite adjacent, what else? The recurring suites and all that. Yeah, you really need to. And the one that's very important actually is the suite, the recurring suite. So that you're actually gonna use them a lot. Yeah, even the suite adjacent as well. Yeah, I'll roughly explain that towards the end. Yeah. Yes. Okay. Yeah. So I'll roughly explain that later on, like the suite arithmetic, sorry, the suite adjacent and the recurring suite. Yeah. Otherwise, you really, those are actually very, very important. Actually, let's do this. I think let me give you guys. Let's see. We'll look at. Let's see. Okay, we'll look at a recurring suites. Yeah, I don't think it's here, so I'm going to like solve it and everything else. That's true. Please pass me my pencil case. My blue pen. Okay, just chill. Let me just turn on my camera so I can explain for you guys these other things.
Sorry, before you actually proceed to the to that part of what start doing, I've got a question on the previous demonstration.
Yeah, sure.
You can kindly just go on that demonstration. So,
Which one?
yeah, like the previous one was from you actually from explaining about the maximum K.
Okay.
Okay. Yes, that range where it says 0 is less than the switch UN, which is less than the inverse of the maximum K. Is that the same suite that is going to be greater than K?
Wait, sorry. Oh my goodness. Where are you? Where?
Just the last sentence.
Okay,
Yes, is that range where it says 0 is less than UN, which is less than 1 over K.
Yeah.
So
Don't.
donk UN is greater than K. So here, if I'm understanding correctly, here the suite UN is going to be less than the maximum. I mean the inverse of the maximum, which is 1 over K. Again, the same suite here becomes greater than the maximum K.
Yeah, meaning that it's going to be okay. Go on. Finish your question.
No, I think maybe if you can just try to explain to me that, I think maybe you can repeat your explanation on that part.
Okay, so in this case here, we know that K is the maximum value of a particular switch you've been given. Then whatever value that is a maximum, whatever value it is, should be a member of real number. Like that's just how it is. That's how it is by definition. So what happens is the first thing here we're given is that we have a limit, which we have a limit of a switch where that's heading towards infinity, and the value we find there is 0. So when you find our value as 0, we also know that the switch should be greater than 0. That's just by definition for the first part. Then because we know that when we're looking at the switch, we have N and capital N. So that has to be defined. And we all know that just from the things we've been looking at, we know that the N, the small n, should be greater or equal to the capital N. Then what happens is that since already we know that 0 is going to be less than the switch UN, meaning your switch is going to be a bigger value compared to your 0, then the inverse of the inverse of your maximum K is going to be greater than the switch. Why? Simply because, let's say for example we have got let's say for example we have okay, let's say the switch, maybe the switch is maybe equivalent to maybe like let's see what, okay, no, I won't actually put numbers there, but yeah. So in this case here, what happens is that when the inverse of K has been introduced, that inverse is going to give us a value that's greater than our switch UN. But then when we're not dealing with any inverse, in this case here, like from this part here, in this case here, our switch here is going to be a smaller value, and this value here should be a greater value. Why? Because the switch here should be less than the inverse of K. Meaning that if the switch is less than the inverse of K, what happens now when you're looking at the K itself and it not being inverse? Meaning that the sign here should change. Why? Because only under inverse can your 1 over K be a bigger number compared to the switch. Under normal circumstances, your switch should be a greater value than the K, because just even by definition, K is the maximum value of the switch UN, what is being initialized there is your suite. Your suite there is a dominant in everything here. So there is no way that your dominant now becomes inferior. No, why? Because it's a dominant. This is why in this case here your suite should be greater than the k. But then what happens is that when you're looking at the inverse of your k, things here should change a little bit. I mean, in this case here, what dominates here becomes the inverse of the k and not the suite. But if there's something that's just under normal circumstances, your suite should always dominate the k, because the k comes from the suite, because without the suite there is no maximum value of the suite. Yeah, this is why in this case here, at the end of the day, we just come to prove that your suite should be greater than your k. Yeah. And what happens is that this very suite here is going to have a limit of infinity. Yeah. So that's for this part here. Yeah. So the reason why the UN is greater than your k is because our k comes from the suite. If we emit this suite here, the k doesn't exist, and therefore that's why it even makes sense for the suite to be greater than the k. But if things change, let's say for example, the way it is here, this k here is now being looked at under inverse. What's going to happen? Meaning that because here it's the inverse of the k, things here should change too. It can be the same way. Sorry. Yeah, it can be the same way as it is when you're looking at it when the suite is just greater than your capital K, your initial K. Yeah, so that's that on that part there. Yeah, so
Wait, so that means that the UN will change when it's an inverse, and the K is going to change when it returns back to the maximum K.
yeah, yes, yeah, just like the K as well changed when it was inverse and when it was not inverse. Things should change because there should be a differentiation when you are looking at the things. There should be a difference. It can't be the same way. So that you're able to know why this is this and why this is that. Yeah. Anyway, I said we're about to look at something else.
I've got a question just there. So like how the suite UN change?
How the suite UN change? If it's an inverse, if it becomes the inverse of this, the inverse of UN becomes 1 over UN, then it's changed. 1 over UN and the UN are different, meaning it's changed. Yeah. So let's say we're going to be looking at recurring suites. Just give me a second. Okay. Yeah, so as I said, we're going to be looking at the recurring suites and how to go about recurring suites. So let me see. I need to okay. So let me just end my just chill. Okay. Yeah. So as I said, what we're going to be looking at now is a recurring suite. So This is 3. Last week we looked at 2 types of sweets. So this time we're looking at a sweet. Hope you guys can see my handwriting. That is re. Okay. So this is the kind of sweet we're looking at today. A recurring sweet. Yeah. So what happens under recurring sweet is that in this case here, we have f. In this case here, we're going to have f, eh? Then now, this f, this f that we have here is going to, by definition, it will have 2 values. It will have an a and it will have a b, eh? And now, this a and the b is going to be a member of real numbers. Just as always, member of real numbers. Yeah. Then what happens is that this f here can be applied in a different way, in a different manner. In the case that, in the case that if this f, if these sort of like brackets, like they change to them being in a curved manner, what happens is you have your a and your b like that, because that means now this f here becomes f, so f will now be in function of the a and the b. Yeah, so that happens here. This is why this and this here are different. This doesn't mean your f is in function of a and your b. This just here means that your f means that f, under f there is something that exists, and you've got your a and your b, and this a and your b are alone. They're different from your f. These two are 2 different things, but this a and the b are members of real numbers. But the moment that you change these brackets to them being curved brackets, what happens is you now say that no, your f is now in function of your a and your b. Is why these 2 here are 2 different things and not the same thing. So you really have to pay attention and make sure that you're not solving things, so you're making a mistake writing itself, writing this, because when you mean this and then you write this, you redefine everything else and it becomes wrong and very inaccurate. Yeah, so yes, yeah. So
No, s'il vous plaît, can you just repeat on the difference?
okay, the difference is that when you're using the curved brackets, you're saying your f is in function of your a and your f is in function of your b. I'm sure you guys have done in algebra, you should have done like how you can expand this and everything else. Yes, yeah. Meaning this f here is in function of your a and your b, but then now when you now introduce this kind of brackets, it becomes different. It means here you're saying that no, there is f. It's like you have a fraction. Yeah, it's like you have a fraction, eh? Yeah. This here is like saying you have a fraction, and this fraction, maybe let's say, is named f. Yeah, sorry. We said no, we have a fraction, then this fraction is named f, eh? And then it's now like I said, no, then now in this same fraction, somewhere there's your a, and then now there's your b. Yeah. And then you now say that, okay, so this a and this b here, they represent real numbers, but it doesn't mean that this a here represents real numbers. Let's say, for example, in this very f, you also have complex numbers. Maybe you've got 3i there, and you've got maybe, such things here. Yeah. So this f is basically just saying that no, in the f here, there's your a and your b, and then this a and your b represents real numbers or is a member of real numbers. Yeah. But that doesn't mean that your f is also a member of real numbers. But what has been defined as a real number is your a and your b in this situation here. Yeah. Yes. Then when you have your f bracket ab, it means your f is in function of a and your F is a function of B. This is the difference. And when you mean this, but then you write this, it's wrong because you're redefining something and you're not explaining it the way it's supposed to be. Because you can't mean, you can't see clearly. Okay, just hold on. I clean my camera. Okay, guys, can you guys see now? You guys can see it. You can see better and clearer this time.
Yes, it's clear.
Yes.
Yes.
Okay, perfect then. Yeah, so this is for this part, just for the first part. Yeah. So what now happens is that since we're looking at the suite, yeah, and we all know a suite is like a suite is written as U and the small n like that. Yeah, this is how your suite is written is. Yeah. So because already like here we know that first and foremost, okay, so for a recurring suite, there's going to be your A and your B, meaning in this case here, there are two things which are involved, A and there's B. Yes, yeah. Now, when we say a suite is recurrent, meaning that a suite is defined by its domain, by its domain. And then now this same domain is a member of your A and a member of your B. Yes. So what happens? So now what I mean is that what you're going to do is in this case here, you're going to say your suite. Yeah, your suite there. Your suite domain, which is U and a small zero there. It's going to be a member of your A and your B. Yeah, you're going to be a member of your A and your B. Yes. And then now, when you try and relate these, let's say like this, we'll say by, yes, yeah, by relation. Yeah, by relation, what happens is that your suite n plus 1 is going to be equals to your f in function of u n there. Is how it's going to be. So this part here is basically defining what a recurring suite is. Yeah. So the first thing we know is that, okay, there's going to be A and there's going to be B. That we know, like generally, that we know. Now, under a suite that is recurrent, we'll now look at the domain. Oh, shoot, sorry. Hold on. Okay. Yeah. We'll now look at the domain of the suite. And that domain is going to be a member of A or B. And then by relation, it's going to be your suites. Yeah, it's going to be your suites n plus 1. Where is that? Your suite n plus 1 is going to be equals to f in function of your suite, of your initial suite. Yeah. And you can write this in a different way. So this whole part here, it's a struggle. This whole part here can be written as, you say n plus 1 is going to be equals to your f in function of your suite going to be in function of your suite, and then that will know that where n is going to be greater or equals to 0, like that there. And then what happens is in this case here, then this is for the first definition. Now for this other, now to define this other part here, it's going to be the domain suite, going to be a member of your A and your B, like that there. So this is for the first part here. Yes.
Sorry, Mona, can you please repeat when you said can be the other way it can be written?
Oh, okay, all right, I'm coming, hold on. Should just give me a second. Okay. So like we say that the domain is normally a member of the A and the B, right? And then by relation, it's going to be UN plus 1 is going to be equals to F in function of the UN. But then this can be written in another way where you introduce now like this huge bracket, and then you say your UN plus 1 is equals to your F in function of the UN. Then you define this UN, you say the N, so you define the N is going to be greater or equals to 0. Yeah. And then this is for this first part here. And then for the other part, yes, write your domain, your suite domain is going to be a member of your A and your B. Yeah. So now in this case here, what happens is that if your F is continuing A and your suite is converging towards L, and we know that L is going to be a member of real numbers, that means your suite L can verify the relation. What I mean is that, let's say, for example, the F that we're given at the very beginning, this F here, yeah, this F here that we're given in the very beginning, if this F here is said to be continuing A, and then now our initial suite that we're looking at is converging, and then we know that this initial suite here, yeah, this initial suite here is converging, and the limit for this suite here is your L. And we know that the L is going to be a member of real numbers, meaning that very L, that very limit is going to be able to verify the relation. Yeah. So what happens is that for us to verify a relation, you're going to say, you do this. You say, if the limit, gosh, okay, if your limit, okay, yeah. Okay, so here it says if your limit, if your limit and your F, if your limit, how do you write and okay, no, sorry. So do this, yeah. So we have the limit, and the limit here is L. So it says if your limit and your F is continuous, and in this case here, we're now trying to find a relation, or rather verify that the UN is actually going to be converging. So what we're actually going to say is that for us to verify that, we actually have to say our UN going to be equals to our L, like that there. This is a way of us just trying to verify the relation between saying limit of N approaching L, then the UN there, because here we've already because in this case here we say that no, this UN here, we know that it's converging, and then it's converging there by definition, and you know there's going to be an F somewhere there because we're looking at a recurring suite. Now this F here is actually going to be continuous and all that. Then we now have to now find the relation between these two and actually verify the relation between the UN and the L. For us to do that, we say the UN is going to be equals to our L there. And then from there, we know that normally how you solve a suite is you have to use the suite UN plus 1, the suite UN plus 1 there. Suite UN plus 1 there. And then what you're actually going to say is you're going to have your L is going to be equals to your F. Yeah, so L is going to be equals to your F. Now this F here is a function of the suite UN, but then in this case here we'll say it's going to be in function of our limit of the UN there. Then this part here it's just going to cancel, making everything become equals, making everything just BL like this there, like that there, that there. Let me see how we'll be able to define that. Okay, so sorry, I wasn't explaining properly. I was just solving. I mean, sorry.
Mono, can you
Yes?
please kindly repeat, because the network had kicked me out of the meeting. Please kindly repeat.
Okay. Sure. So what I had said is that we have the suite, eh? We have this suite here. So we under a recurring suite, we know that it's going to be like this. We have this here is your domain of the suite. It's the member of A and your B, and then by relation, it's going to be UN plus 1 going to be equals to F in function of the suite UN. Then now this whole thing can be rewritten like this, where you say your suite UN plus 1 going to be equals to F in function of your UN. Then you have to now define what our N here is. As usual, in Analyse, you need to define sorry, just hold on, give me a second. Okay, you need to define it, so we know that our N is going to be greater or equals to our 0. Then usual for our domain, just say our domain is just going to be a member of A and B. And now what happens is that for us to now like further, for now, okay, this is sort of like one of the prepositions that's there under a recurring suite, is that you're going to have your F. You're going to have your F, and that F is going to be continuous, and your suite is going to be, and your suite is actually going to be converging. And you know that for us to now prove the relation, because already we know that by the things from the things we've been looking at, we know that normally when you've been given a suite UN, our limit is going to be L, and that L should be a member of real numbers. Now in this case here, we know how to find the relation between the suite and we have to prove the relation, or when we find the relation between the suite UN and the limit, and its limit L. So in this case here, what we're going to do, because here the only thing we've been told here is that the F is going to be the F is continuous and our suite is converging. That's the only thing we've been told in this case here. So what actually happens here is that you're going to equate you are going to equate your suite UN to your limit, to the limit, to your limit L, and then now you're going to now have your initial limit now will now change. It'll be like this. So what happens is that the first thing for us
just a second before you go any further. You said the limit is converging. What did you use to tell that it's converging?
In this case, we were just told that it's converging. In this case, in this case here, like we're just told it's converging. What is it when suite is converging? Okay, let's say for example, you're looking at a graph. How do you know that a particular graph is converging and is diverging? That's how you know. That's the same application you use when you're looking at a suite. When you look at it converging and when it's diverging, it's the same concept. When you're trying to differentiate, when you're looking at different graphs, when your curve is going one way, your curve is going the other way, use the same concept for you to define a converging, if it's converging, diverging, whatever it is, according to, normally you would use like what sector it's in. Is it in a sector that's only positive values, negative values, or it's in the middle of both negative and positive values, and the same thing. So like normally one of sort of like the tricks or ways to know that it's converging sometimes is maybe like if you found something that's positive, or how I know it's diverging at times is if you found something that's negative. That's one of the tricks for you to know if it's diverging or if it's going to be converging. That's just one way for you to know that it's this and that it's that. But normally, how you know something is diverging or converging, you have to apply the same concept you apply when you're looking at a graph. How do you look at a graph and the curves? Yeah, I know that. As we move forward, I don't know how far you guys have gone in your TDs, if Enes has already explained for you converging and diverging, but there is a lot more, there are a lot more concepts and other like ways for you to know, like as you move forward, like the topic we're about to go do, which now is like further details of limits. Yes, yeah. But one of the ways how you know is according to the values that you have. Yeah. So, yeah. Then, in this case here, for us to find the relation between the UN, it being equals to our L in this case here, what we're going to do, let me just put this down. Okay. What we're going to do here is that, this is going to have its own limit, and the limit we're going to put here is going to be UN plus 1. We'll just put this limit just like that. We'll just say, no, this will just have a limit of UN plus 1, eh? Yes. So now, if we put the limit, sorry, let me do this. Put it on the table, let's put it that way. Yeah. So make the limit be our UN plus 1 in this case here, right? Okay. And what we're trying to look at, or prove, is the relation between the UN is equals to the 1. So the first thing we say is our limit is going to be UN plus 1. This, guys, here has come from what we looked at the beginning, where we're looking at the F and everything else. And then, then what's going to happen is that in this case here, we're going to bring our L. Yeah, we're going to bring our L here, eh? Then we'll say this L is going to be equals to our F and in function of the UN. And then this UN here is also going to be a limit. So it's going to be, let's put limit. Okay, let's put limit here. It's going to be the limit as well of the UN. Remember that this was actually in our initial question, it was from here, this part here, you've seen it? Because here, if you put limit here, meaning also here, you should also put limit here. You see, the limit was n plus 1 here. Whatever we do here should be done this other side here. So even here, we're also going to introduce the limit too. Then we're going to equate this to it being L for this part here. Yeah. Then at the end of the day, we are just going to cancel whatever function, whatever limit that's there, and we're going to remain with our L. Because in this case here, let's say our limit here is going to be, because, okay, it was, remember at the beginning it was n plus 1 is equals to f un, right? If here let's do this, we put limit here. This limit here is going to come here and also going to come here like that here. This is how we have the limit of this first part here and the limit of this other part here like that. And now these same limits are going to be equals to the L. What happens is this will cancel, like this here will just be like, it's like you don't value this anymore. They end up just remaining with your initial L, just like that there. And this is how we're able to prove or verify the relation between the suite and the L, which this L here represents the limit. Yeah, just as we all know, like usually how it is, and under normal circumstances. Yeah, this is like one of the first prepositions. Yeah. So I'll put, let's say I'll put 1 here, I'll put P1 here like that there. Okay. Then now P2 have a second preposition. Yeah, have a second preposition. Our second preposition or theory, whatever it is we're going to go back to the fact that we know that our F from the beginning has got A and our B, right? Now these are members of real numbers, isn't it? And then from here we know that, our F, our F is going to have our A. Our F will be function of the A and the B, eh? Yes. And then from there we know that this A and this B are sort of like together. So just put our C there, and then we'll put our A and the B there. So this literally here has been redefined here, sort of, yeah. And then this is just for what we've been given. Then now, for the first point, our first point there, we're going to suppose that our F is croissant. So we'll say our F there is going to be croissant, right? Then under A and our B. This is the first thing we're going to suppose. This is our first supposition. Yeah. So what happens is that you're going to get your suite. You say your suite 1. Sorry, please, what's my Tipex? Hello, Tipex. Thank you. So, sorry. Okay. So, our first thing we'll suppose is, so here we'll say, just check, give me a second. So, okay. So the first thing you will suppose is that our F is going to be croissant under A and your B. Yeah. So what happens is that in this case here, we're going to say if our first suite, so we'll say, since it's our first suite, so we'll just name it as U1 because it's our first suite. It's going to be equals to the function of our suite. Remember, our suite is like, if it's a function, it's going to be F in function of our UN like that there. Now in this case here, since our suite here has been named, so in this case it's going to become our suite, going to become U. And then like, remember how last time we were solving it, like when it was 1 here, it became like, yeah, it was 1, it became 0 the other side. Yeah, the same concept. So it becomes 0 there like that. So cancel the name for there. We know that it's going to be greater or equals to 0. And already, because the 0 here, it's already automatic that there is going to be 0. Yeah, for this part here. And yeah, so this is the first thing. If maybe the value, let's say for example, if our value here was -1 here, right? And maybe here it was, yeah, if our value, okay, let's just forget this part here. But then we suppose that it wasn't going to be U0, but maybe U-1, and then they put this, meaning that this wasn't going to be croissant. But then because we found our 0 here, or if we were able to find any value that's greater than 0, meaning that we've proved that when you have been given a suite 1, whatever it is you find under A and your B, whatever value you find here, your suite here is also going to be croissant. This is why in this case here, this suite 1 is going to be croissant, because it has been able to prove itself under this way. Yeah, because 0 here is going to be 0. It's 0 here, and like this suite here, if it's going to be 0 here, meaning this light thing here is also going to be 0, and 0 is going to be equals to 0. And if maybe here the value you found here was maybe 2, and we suppose you found 2 here, and mean 2 is greater than 0, and this Q is going to prove that this F, that our function F is actually going to be croissant under A and B. Is that for this reason, this case here, our F function in our suite here is going to be croissant, because it has been able to prove itself that the U0 is a member of the 0. So it is equals to 0, because it's proved that suite 1, which is equals to the function of suite 0, is greater or equals to 0. And when you look at this part here, automatically to give you 0, and 0 is equals to 0, and it's been able to just prove itself, and that's how it is for here. Yeah, you know, it is what it is for this part here. Yeah, so for this part here, yeah. Then for suite 1 here, then now there are times, when let's say for example, we'll still use our suite 1 there like that, then we'll say maybe like whatever value we found, maybe here we found, okay, I don't know, whatever value we found here, maybe let's say we found okay, let's say we found -1. We found -1, meaning that -1 is going to be less than 0, meaning that the suite U1 is going to be less or equals to 0. And then when it's less or equals to 0, meaning that this same suite here becomes the croissant, because in this case here it's changed. It does not go with the property of it being greater or equals to 0. In this case here it's changed. So it depends what you find when you have solved it in function of whatever suite you've been given in this case here. Like in this case here, what happened is that here, our suite, like here, it was our suite U1, when it was in function, when we solved some things, we suppose that we solved some things, and whatever value we found here, when we solved it, we found 0, meaning that 0 is going to be equal to 0. And this does go with what we are trying to, sorry. Hold on. Okay, yeah, it does go with what we're actually trying to find. And in this case here, it's going to be equals to 0. Now, let's say, for example, we still suppose that we were still looking at the switch U1, right? Yeah, the switch U1. Then let's say like we solve some things and maybe we find the answer is -1. -1, guys, is smaller than 0. So in this case here, the switch here is not going to go with what it's supposed. The switch here is not going to go with our property that it should be greater or equals to 0. In this case here, it becomes less than 0. I mean that because it's now changed, it now becomes decreased. So even that's by the value that you found. So those two are examples of just properties. Sorry, yeah, of the properties under this first preposition. Sorry, under the second preposition. Sorry, this preposition here. Yeah. So in this case, we just supposed, so we can just try and like have ideas and everything else. Yes, yeah. So, and then like at times, what happens is that, let's say for example, you can suppose that, because in this case here, we suppose that our F was croissant. That was our main point. Our main point here was for us to prove that our F is croissant in this case here. Now let's say in this case, we suppose that our F is going to be decroissant. And how are you going to do that? The first thing is that when a switch is decroissant, when your F is decroissant, what happens is that your switch is not monotone. Yeah, it's not monotone. And then from there, you have to solve some other things and all that sort of situation and all that. Gosh, I feel so tired. Anyway.
So, you talked about the other things. Will you also show us the other things which are supposed to be solved?
Oh yeah, yeah. I'm about to solve an example.
Oh, okay.
Yes. So okay, let's get rid of this paper and get a new paper. Okay. So we're going to look at a suite. I know whether you guys have already done such an example before with NS. I don't know how far you guys have gone, but yeah. So what happens is that wait, let me just fold my paper. It'll be more convenient to fold the paper. Ish. Stomach is the ghetto. Ooh, okay. Okay. Hope you guys can see. Can you guys see? Ish. Okay. Yeah, you can see. Okay. So this is example 1. Yeah. So, okay. So our question here, we've been told to study a suite. Now we've been given that UN plus 1 is going to be equals to the square root of 1 plus UN. Then now we've been told that in this case, so it's like this. So we're told that our suite U0 is greater or equals to 0. Yeah. Have you guys done something like this with NS? Before I waste time and solve something that you've done.
No, I haven't.
Okay, so when you've been given a suite like this here, guys, is a recurring suite. And under this suite, there's a way. Sorry. Let me just see the okay. Oh, someone asked for like a sketch. Oh, I'm so sorry. Okay, I'll go back to that and I'll do that, and I'll do a sketch and everything else. Yeah. So we've been given this question here, and you've been told to study the nature of the suite, and this is all we've been given. So what happens is that under this, the first thing you have to do is, guys, there are steps here you have to follow. Remember, this here is a recurring suite, and under a recurring suite, you know that somewhere you're going to have to involve like a function of something and everything else. So the first thing you do, the first step is that what you're going to do is that you're going to get this part here. Yeah, you're going to get this. You're going to get this part here and make this
Hello.
being x.
Hello.
Yeah.
I'm a bit behind.
Okay.
Just want you to explain for me.
Mm-hmm.
You are actually calling that U0 to be a domain. I don't really know what it means.
What it means to be a domain. Let me say, guys, how someone to explain what domain is. They don't know how to explain that. I don't know how to explain what a domain is. So let me Google what a domain is. Domain, guys, I don't know by definition. Hold on, give me a second. Domain. Just true. I think it would be easier if we actually able to just I don't know, what's this, please? Hold on. Cancel that. There. Okay. Let me see. Domain in math. Okay, normally like a domain, let's see. Okay, like generally like domain just means like the main territory, like under like normal circumstances. But in math, okay, I think how am I going to put this? The domain. Okay, no, yeah, I get. So let's say for example, you are looking at okay, let's say you've been given a set, eh? Then like in that set, you have been given maybe 1, 2, 3, 4, 5 in that set, right? Now what happens is that let me just do this. Okay. Yes. So let's say for example, this here is your set. Let's say this box here is your set. Eh? Now in this main set, we have your A, we have B, we have C, we have D, right? You've got 4 different sets which are in a main set. And normally, one of this set is going to be the universal set. Yeah. So what happens is that, sorry, just joke. Sorry. Okay. Yeah. So what happens is that since we know that like just like to define domain generally is just basically like the main territory or someone like having territory over something else, like domain superior, like that. Yeah. So let's say for example in this case here, you've got your A and you've got your B, and then now like so you got your A and you have your C, and then now your C is found in your A, right? Meaning that this C here is going to be it's a part of your A in this case here. Let's say this A here is a village. Eh? Now in this village here, there's now a little group of people. Now these people here are called C. These people here are called C. What's going to happen is that if they are going to ask here, no, between these two here, which one here is the domain of the other, it's going to be the A. Why? Because the A is one that like it rules over, it's one that's superior to the C. So now in the case where we're looking at, in the case where we were trying to redefine what a switch recurrent is, what happens is that for a switch recurrent is that you need to have a switch that's dominating the main switch. Now this main switch has a symbol of the U, of this U here and this 0 here. Eh? That means this switch here is one that's dominating. It's the main switch. Yeah, it's a main switch here that's dominating. Now this very main switch here is going to be called the domain of the switch, which is going to be the U and the 0 here. which is going to be a member of the A and the B in this case here. Then now what happens is that this same domain, this same main suite here, this major suite here, it being a member of the A and the B here by relation, by relation it's going to be the suite U, then it's going to become n plus 1, going to be equals to the function of the initial suite here. So what happens is that this suite here is an initial suite, the domain. This one here, then this here is just like how you try and solve suites. Normally you look at it in this way. This is how you actually like bring it down. Normally this actually acts even as a formula as well. When you're solving suites, you're going to be using the suite U n plus 1. Even like questions, they're normally going to give you n plus 1, like to represent a suite and everything else. So that's a domain for that. I don't know whether you want me to re-explain the whole thing or I should just go on with the question. I don't know.
It is clear. Again, then how did you know that that suite we were about to answer it is converging? Because as far as I'm concerned, I was thinking that you only get to know a type of a suite after working it out.
In this case here, they gave us the information. They told us that the suite was converging. It was already told. It's not like no, we know how to figure it out. In this case here, we were told that no, it's converging. It's different when you've been told and when you haven't been told. When you've been told that it's converging, meaning that you now have to prove that it's converging. And like when they just give you a suite, then it's now your job to now find if is it converging, diverging, is it monotone or not monotone, is it what, croissant, decroissant, all those things. So it depends with how the question is, the info you've been given, and everything else. You've heard? Should I don't know, should I go on or someone else still has a question before I start to explain this? The thing is, I won't even finish this now because it's very, very long. Let's see. Okay, no, we'll do this. So this same question I've given you, this same one here. So this same example I've given you guys, this one, I'll leave it up to you guys. We'll do this. We'll leave it for Friday. Friday, as we come on Friday, I'll solve it nicely. But I want you guys to try. Yes, I want everyone to try and solve this suite. You try and solve it, and then you send me your try of your calculations before Friday. And then on Friday I'll come and then I will re-explain everything, because now the time is not enough for me to explain this, because this suite, as this sort of question is very, very long. It's a very, very long question. So even before I solve, I know the time here is not enough. So I want you guys to go, you try and you solve, try and do some research. I don't know. Yes, then you solve it, then we come back Friday. I'm going to explain it, but then do make sure that you actually do send me your calculations before Friday. Anytime before Friday. You've heard?
Sorry, what are we supposed to solve?
The question has been given. You've been given, it says un plus 1 is equals to 1 plus is equals to the square root of 1 plus un. Then you've been given that u0 is greater or equals to 0. Then now you solve.
So what exactly are we solving for? Like, what are we doing?
You have to study the nature of the suite.
But you said that this suite is already been voted that it is converging. So me thinking that there is something.
Wait. Before you go any further, this here is a different suite. This is a question. This question, this is an example. This one here is different from what we're talking about. So this question here is separate from the other things we're looking at just now. The other things there we're looking at different from this question here. This question here, there's no info of it converging, diverging, what. No. The info here is different. In this case here, it's us to now find the answer, you know? And like the other things, okay, let's do this. I'll start. Yes. I'll start, and then you guys will finish. Right? That's okay, huh? Yes. Perfect. So the first thing is, what we do is that you have to write this whole suite, this whole part has to be written in function of f of x. That's the first thing you do. So what you're going to do here is that you're going to say f of x is going to be equals to the square root of 1 plus x. You see that, eh? What happens is that in this case here, your suite un will change to x, because now it stopped being a function of un. No, it stops. Now this changes to this. That's the first thing you do. Then now, after you've been given, you solving it, or rather changing the things to it being f of x is equals to square root of 1 plus x. The next thing is that you now have to like define this. Yeah, you have to define this. So I'm sure you guys have done this how to redefine this in algebra. Yes, so what you do is you're going to say x is going to be a member of df. Yeah, and then from there you say going to be equivalent to, because here you have 1 plus x here, so you're going to say 1 plus x is going to be greater or equals to 0. Then now the same thing here, now when you say it's going to be equivalent to x is going to be greater or equal to -1, because when this comes here, it becomes -1. This is why it's -1 here, before someone else comes to ask me. Yes, yeah. So you begin that there. Oh, sorry. Yeah. Okay. No. Just chill. Sorry, this I have to write it this other side, not down here, because it would look as if it's a part of this other thing, but it's a continuation of this thing. So this, when this comes this side, it becomes x going to be greater or equals to -1, because that there negative, you know why it's like this. So we've done this, the first thing. Yeah, then after doing that, now we now have to like see, no, where is this from? Because x here is greater or equals to -1. So what happens is at the certain point here, we now have to now define this. It's this. We have to define this here, has to be defined now. This part here has to be defined. So what we're going to actually say is that we're going to say domain function of that is going to be equals to that, since -1 here is a certain point, so -1 there, like that there, and then comma, then where is it? Let me see where this heading. X is going to be greater or equals to -1. So in this case,
Mono,
ma, yes,
what does the D mean?
the D mean
Yeah,
domain
that
function.
DF.
DF, domain function.
Okay.
Yes. So I'm sure you guys have done this in wait, no, have you guys done this, but like how to like write this like in this form, like how to redefine this in this form? Have you guys done this in algebra already? Haven't you done this? Huh?
No, we have not.
You. Sorry, sure. Sorry, screen. Yeah. Okay, you haven't. Anyway, you do it eventually. Inshallah. We'll see. Yeah. So you've redefined that this here goes to this. It's like this because -1 here is a certain point. So it starts from -1, eh? Yeah. And then, so yeah, by the way, guys, whenever you've been given such a question, this is how you start. You always have to first write your suite in function of f of x. Then from there, you need to simplify whatever it is you've been given in a way whereby you're able to rewrite it like in a group, like as well about like write sets, sorry, like where it's a domain function is going to be equals to their -1 and then positive infinity, then what does this here mean? This here actually means that this part here has been redefined as our starting point, meaning that the numbers here we're looking at under this domain function is going to start from -1, and we end up to whichever value that's it is, as long as the value is positive. Yeah. And then what happens from here is that since in this case here we're looking at it like under A and under B, so you can also like write like this whole thing. You also say no, A, B, like that, they're going to actually be equals to, then from there you start from 0 and then comma and then that there and everything else. But this, just don't mind this, but this, you should mind this. You have to know how to write these things. You have to know how to write this thing. You guys looked at what it means when you have these kind of brackets. Yeah, you have to know how to write this in this way. And then there are times when you are going to be given something, you'll find something like this, but then you have to now write it in 2 different forms or 2 different ways and all that. Yeah, so it's the main function is going to be equals to -1, positive infinity there. And then from here, what happens is that you're going to go back. Yeah, you're going to go back to this. Then now, in this case here, we now have to like solve it in a different way. So what we're going to do there is that we'll say f prime of x is going to be equals to, let's say this here, this is actually equals to saying 1 plus x to the power 1 over 2. These guys here that we already know, don't we? Yeah, this here we already know this is equals to this, and then we now solve that there. That's this here is going to come down there and everything else like that there. Yeah, that's going to become 1 over 2 that 1 plus x there. This is going to be prime there. This over there square root, we still maintain there the 1 plus x there like that. The 1 over 2 like that there, square root of 1 plus x there. Yeah, no, that's yeah. Then for therefore have going to be equals to 1 over 2 square root of 1 plus square root of 1 plus x like that there, because this there is the one there. This here, not that there. This here, I'm solving here. Prime this, there, that. Yeah, direct. Yeah, it's very direct actually. Yeah. So what is that? This is equals to this is the same thing as writing that there, right? You now find the. Let me see, guys. What's the English word? Sure. Hold on, I'm going. Okay. Yeah. Let me see. What's the word? Ish. Okay, anyway, I'm putting the word, you guys. But you guys remember, I think it's first principles. Yes, yeah. First principles. You guys remember, is it first principles or second principles? You guys remember that? Hello?
In terms of what exactly?
In math.
Is there any specific topic that
You remember how like you guys would solve limits? Like you solve limits using the principle, you use the method of first principles. Do you guys remember that in math? I don't know if it's also
Yes, now some of us thought that it will never be in use, so we never really paid attention to it. We had used other means of ways.
oh yeah. Mado. Okay, okay, so this is why I told you guys to solve limits, you see? Yeah. This is why you guys have to solve a lot of limits. because this, yeah, because you have to actually like use those. Remember, you guys know that when solving limits, you use different ways, eh? The different ways of solving. I hope you guys can remember how to integrate. You remember that, right? You guys remember integration?
Yes.
Yeah. All those things, integration, what, all those things. Very soon we'll be using all those things. You guys should make sure you go through all those things and do go through limits, please. Limits, you're actually going to use a limit. Those same principles used to use, except first principles is a little bit too complicated at times. There are easier methods for you guys to actually like solve limits apart from using first principles. You can use what method is that? What method is that? Ish. Let me see. Where you find the what's that? Guys, I've forgotten the word, but otherwise, yeah, under solving limits, there are many methods apart from first principles. Things I can remember first principles in my head. The other ones, like by name. The other ones, I can't remember the names, but otherwise, yeah, you guys really need to go through first principles. And this part here, we're not done. I think I can't like go further if you guys cannot remember like how to solve limits and everything else, because you kind of need these things and all that. But yeah, so we'll do this, you guys. This time, make sure you go and then you actually like look at limits and you try and solve even just 2 limits. Just solve 2 limits. You solve at least you know how to go about it. Yeah, so that on Friday when I come and re-explain this part here. But I still want you guys to at least try and continue and finish up how you actually like solve this thing, It's very, very simple. It's very, very simple. And the good thing is that such a question, the way the formulation is the same thing, the same concept. If maybe here they just give you 3n plus let's see what, let's say they give you 3, okay, whatever it is, you will still do the first thing, f of x, same thing. Next, domain function. Next you further simplify it. From there you get this, you redefine. Guys, it's the same thing, the same way, except the values will just change. Here it will be 3, there it will be what, here 7, here what, here what, here what. Otherwise it's the same concept, there's no difference. So do make sure that you actually do go through the limits and how to solve limits. Yes, but otherwise I want you guys to continue from here. You further continue. What you're going to do is how you're actually going to continue this. Actually, from this part here, everything I was from explaining where we looked at the L, the what, F is continuing and everything else, all that proving. Oh, I forgot the next. Sorry, what? Oh, okay. Oh, thank you. Yeah, both the negative and differentiating. Yeah. Yes. So do make sure you guys go through differentiation, guys. It's very simple. Yeah. So what was I saying? Yeah. So all those things I was talking about, where F is going to be, where F is continue, where what from this point here, what you continue with is now applying the things we are from doing just now in this equation we found at the end of the day. And then make sure that this time around, you have to now know how to go about it and whatnot. So from here, you apply everything we're from looking at under a recurring suite. From here, this is what you're supposed to do. So make sure you go and you apply, and then you shouldn't forget that we'll just end there. From here, start applying the step by step what we did. You begin to apply it from here. Yeah, so I want you guys just try and just apply the notes and everything else, and just try and solve. And then from there, then you can send me like what you're going to find and all that. Yeah. So what we'll do is on Friday in the morning, we will let's see. Okay, yeah. Friday in the morning we'll first Friday in the morning we'll first look at one more example like this one, a different way, different example, but like this one here. Yes, so that at least the understanding is going to be more deepened and like, yeah. But otherwise, I want you guys to just try and apply the notes. I want to see if you guys actually do understand the notes. This is why I'm not going to go any further, because I want to see if you guys do understand the notes and how you apply your notes with what you've been given. So that's what I want you guys to do. I will not go on and solve it for you. No, I want you guys to see if you guys understand the notes. So from this point here, do apply the notes and everything else. And yeah, then before Friday, you send me whatever it is that you found. Yeah. And then there's someone who asked me for a link to YouTube videos and the Analyse. What you do is that just search for whatever it is. If you're looking at limits, just search limits, how to solve limits. It's easier that way. Yeah, it's easier that way. I can't really remember. I try to remember like the links, so the videos I used to watch, but I really can't remember. It's been so long since I've done Analyse that I can't remember like when, like what YouTube videos I actually used to watch to fully understand. But just try and just search for whatever it is you're trying to find, be it sweets, what you find everything there. Just search on YouTube, just whatever. Yes, yeah. I really can't remember. I tried to go through what ish. I can't remember. Yes, yeah. So that's that. And from here, guys, make sure apply the notes and everything else that we're from looking at. You apply everything here. Yes, yeah. The way I was writing was a little bit rough, so I don't know if you will see, even though I send the photo. And everything.
Yes. Just send, even if it's rough, it's okay. It will do something.
Okay, right. Yeah. Otherwise, unless you guys have any further questions.
Yes, I've got a question.
Uh-huh.
You mentioned something about using the first principles. Well, is it also part of the calculation that you're going to be using in that question?
Oh no. Oh no, it's not. No, it's not. Like yes, like like at times when you're solving sweets, sorry, when you're solving limits, there are times when like you would use first principles and other things. Do you remember? I don't know whether you guys can remember.
Actually, I remember.
Pardon?
Personally, I do.
Yeah. So yeah. Otherwise, I'm sure you know that there's simpler ways of solving limits. No, at times like first principles at times is complicated. There's easier ways for you just to differentiate and just solve and all that. So you don't go through all those things. Yeah, the easier methods actually. But yeah, the others who find first principles like easier. Yeah. So yeah, but make sure that you actually do solve your sweets and yeah. Solve some sweets, guys. Even just one, even just two, so you just remember how to go about these things. Yes, yeah. Otherwise, that's that. The question, I hope you guys already know. We'll do this. I'm going to send you guys a photo of where I ended. You continue from here, from where I've ended. You apply the notes, you apply what we looked at there. Okay. Yeah, you're going to apply what we looked at in your calculations. Actually, find the answer. Yeah. By the way, guys, make sure each step is very vital, very, very important. Yeah. So do make sure to apply each step and don't forget any step, because what happens is that whenever you're looking at such a question, once you miss out one step, the whole goddamn question becomes wrong. Your whole calculation is just wrong. Yeah. So do make sure that you do that work and you try. The point is not for you to get it correct. No, the point is for you to actually attempt to actually try to solve, to try and apply the notes. That's the whole point. That's the whole concept behind everything, is for you just to try and apply the notes. And notes to get it correct. Application is what's important. The moment you're able to actually try and attempt to solve something, you make your work much easier. Yeah. So do make sure you try, you solve, and yeah, and you do send me the, and you do make sure, guys, before Friday, send. Guys, actually, let's do this. It's just one question. That's one question. By Thursday in the afternoon, Nishi, all of you you've all tried. You've all tried to apply the notes. You send me your tries. Your answers, name it. Before Thursday afternoon, I want to see. Okay? Otherwise, you guys should enjoy the rest of your evening and you take care of yourselves and do make sure that you do what has to be done and you enjoy. Yeah. Otherwise, bye. And